It takes about 2 seconds. You type a question into an artificial intelligence, and the answer streams back onto a glowing screen. It feels like nothing. Weightless. But in those 2 seconds, your question traveled to a building you will probably never see. We're only shooting the football that's refuelicate Riovan Humacius infused other man. A building the size of several football fields, packed with racks of specialized processors, drawing as much electricity as a small city. A building engineered from the ground up around a single physical problem: removing heat. This film asks one simple question: what physical infrastructure is actually required every time someone uses artificial intelligence? Artificial intelligence feels like software, an app, a chat window, a voice. But software has to run somewhere. When you press enter, your prompt leaves your device as pulses of light inside a fiber optic cable. It races through local exchanges and long-haul networks and arrives at a data center, a warehouse built not for goods, but for computation. Inside, your words become numbers. They pass through a neural network with billions of parameters and turn back into language. For you, it is a sentence on a screen. For the building, it is trillions of calculations, and every one consumes electricity. A data center is organized around one thing: rows and rows of server racks. In an AI facility, the machines that matter most are accelerators, chips such as graphics processing units or GPU. A GPU performs thousands of simple calculations at the same time, in parallel, which is exactly what neural networks need. A modern AI chip can draw around a kilowatt, the peak power of a microwave oven. One server holds 8 of them. But no single chip is enough. Modern AI models are trained across thousands of GPUs working at once. That only works if the chips can talk almost instantly, through specialized links inside each rack and fiber optics between them. The network lets thousands of processors behave like one enormous computer, while storage systems feed them oceans of training data. Around the computing sits everything that keeps it alive: a dedicated substation, transformers, switchgear, uninterruptible power supplies backed by battery. Standby generators wait for the rare moments the grid fails, and layers of monitoring and security watch it all around the clock. So what makes AI different from the ordinary cloud? The cloud that stores your photos spreads lightwork across many machines. A typical cloud rack draws 10 to 30 kilowatts. AI concentrates work instead. The current flagship AI rack wires 72 GPUs into one unit, drawing around 120 kilowatts, roughly 10 times a conventional rack. It weighs about 1.5 tons. Floors have to be reinforced. Power systems have to be redesigned. Training is also strangely synchronized. Thousands of GPUs surge and pause together, swinging demand by tens of megawatts within seconds. Engineers have added batteries and software just to smooth the load the grid sees. AI changed how these buildings have to be built. All of it runs on electricity, and electricity has become the industry's defining constraint. In 2024, data centers consumed an estimated 415 terawatt hours, about 1.5% of the world's electricity. The International Energy Agency projects that could more than double by 2030, though it stresses the range of outcomes is wide. The United States, around 4% of national electricity in 2023, projected to reach between 7 and 12% by 2028. In Ireland, metered data shows data centers already using more than a fifth of the nation's electricity. But the problem is not only generating power, it is connecting it. In America's largest grid regions, projects can wait 5 years or more. So operators go to extraordinary lengths, siting facilities beside power plants, signing 20-year deals to restart a shutdown nuclear reactor. Some have ordered small modular reactors that have never been built commercially. Where the power is now decides where the machine gets built. Then there is a rule you cannot negotiate with. Almost every watt entering a computer chip leaves it as heat. A 120 kilowatt rack is, in effect, a 120 kilowatt heater. A single hall may hold hundreds of them. For decades, moving air was enough. Cold air pushed through the front of the racks, hot exhaust captured and cooled again. But air cooling struggles beyond roughly 40 kilowatts per rack, so the industry is switching to liquid. Chilled water loops carry heat out of the halls. Cold plates press against the processors themselves, with coolant flowing through them. This is direct-to-chip cooling, how the densest AI racks survive. Some operators go further, submerging entire servers in tanks of fluid. Each approach trades cost, energy, and water differently. Evaporating water saves electricity but consumes water. Closed loops save water but need more power. Per prompt, the water involved is tiny. Multiplied by billions of prompts a day, it has become one of the industry's most scrutinized numbers. Why build all of this? Because in artificial intelligence, computing capacity itself has become the competitive edge. The 4 largest American cloud companies reported combined capital spending of roughly $400 billion in 2025. Most of it went here. And they have told investors to expect substantially more. Beyond the money already spent, far larger numbers have been announced. Multi-hundred billion-dollar campus programs. Single sites plan to draw as much power as entire cities. But announcements are not buildings. Some exist only as land, permits, and press releases. Yet the construction underway is real. One of the largest private building programs in history. So what could slow it down? Almost everything, in fact, except ideas. Advanced chips are limited by a handful of factories running at full capacity. Giant grid transformers can take years to procure. Gas turbine order books stretch toward the end of the decade. There are not enough electricians. Grid connections queue for years. Communities are pushing back too. Dublin has effectively paused new data center connections. In Virginia, county battles have stopped projects in court. And over all of it hangs a question nobody can answer yet. Will demand for artificial intelligence grow into the capacity being built? Some call parts of the boom a bubble. Others call it the largest infrastructure build-out in human history. Both could be partly right. Back at your desk, the cursor blinks. You type a question, and 2 seconds later the answer arrives. Fluent. Instant. Apparently weightless. But now you know what those seconds contain. Light in glass fibers. Thousands of processors in lockstep. Megawatts of electricity. Rivers of coolant. Artificial intelligence looks like it lives in the air, but it lives in a machine, a vast, physical machine. One that had to be financed, permitted, powered, and cooled before you ever pressed enter. Subscribe to Hidden Systems for more cinematic explanations of the infrastructure behind the modern world.